Hi everyone, my name is Ulises Xolocotzin. I work at the Mathematics Education Department at CIMBESTA in Mexico. First of all, I would like to thank you for your interest in this talk. And I also want to thank to the organizers of PMENA 42, Ana Isabel Sacristan and Juan Carlos Cortez. The title of my presentation is Eye Tracking the Effects of Visual Representations, Linking Vision and Mathematical Reasoning. I will be talking to you about the work that I do with my colleague Matthew Inglis from Loughborough University and my colleague Ana Medrano, who works with me at CIMBESTA. So let me start with the current state of eye tracking in mathematics education. In the review published by Strohmeyer last year, we can see how the number of studies that employ eye tracking methodology has been consistently increasing over the last decade. I think this has to do, in part at least, with increased availability of eye tracking hardware and software. It is much easier to work with eye tracking nowadays than it was 10 years ago. And that's interesting because we are just starting, and that's important. It means that we are just starting to learn how to use eye tracker, how to use eye trackers for studying the learning of mathematics. And in particular, I will be talking about eye tracking the effects of visual representations. In the review by Strohmeyer, it was surprising for me and for us, for my colleagues and I, to find out that the study of visual representations with eye tracking methods represents only a very small portion of the published papers that employ eye tracking methodologies. And it is surprising for us because visualization is a very important topic in mathematics learning. Visualization is everywhere in mathematics learning. It's in materials, in books, problems often involve visual representations, and also visualization as a cognitive process plays a very important role in mathematical thinking. I think Arkabi explains this better. He says that visualization is the ability, the process and the product of creation, interpretation, use of and reflection upon pictures, images, diagrams in our minds, on paper, or with technological tools, with the purpose of depicting and communicating information, thinking about and developing previously unknown ideas and advancing understandings. So as we can see, visualization is a very important part in mathematics, plays very important roles in mathematical thinking. So to illustrate what eye tracking methods can tell us about the relations between visual representations and mathematical thinking, I would like to mention three findings. The first one is was made by is reported in this study by Atagi and colleagues, who found that students incorporate visual representation with symbolic notations when this information is provided. That is, if you present students a problem in symbolic form and also a visual representation to support the solution, the students will integrate this visual representation. That is, they will look at it, but only if this visual representation is actually helpful for making a correct response. Another finding that illustrates very well how eye tracking methods can be used is the one that was reported by David Bolton and colleagues. They found that some representations are more adequate for specific domains. In this specific study, the authors found that some representations are more helpful for helping students to find correct solutions to multiplication problems. Um, Even if representations are present the same information, for example, comparing two models of multiplication, one with one which is like which is a number line, and another one which is a rows and columns model. Those both models present the same information. However, the number line representation is less effective for supporting students in producing correct responses. And this is why the number line concentrates the attention of students only in some parts of the multiplication structure. And that's something that you can observe only with eye trackers, with eye tracking, by tracking eye movements. A third finding that I'd like to emphasize is this one. Wei-Kwang Li and colleagues found that the integration of text and figures, it's always text directed or tends to be text directed. They found that if you present students with diagrams and some text explaining a mathematical situation, students will use the text for making interpretations of the diagrams and not the other way around. That is, students will always start by reading the text, and then will go to the diagram and then go back to the text and so on. And I think that's an important finding, because in mathematics education, materials like textbooks and problems and even in digital technologies, there are always combinations of texts with visual representation. That is, what I mean is that visual representations are very rarely presented without text. And what eye tracking methodologies can tell us about how students integrate text and visual representations is that the text seems to be telling students what to do with the visual representations. So text is always a referent that tells the students how to use the visual representation, and not the other way around. So these are really interesting findings. However, there are still many open issues in the study of visual representations with eye tracking methods. One of the most important ones has to do with interpretation of eye tracking data. The mainstream interpretation of eye movements is that visual focus equals cognitive focus. This is known as the eye-mind assumption. And what is problematic about this interpretation is that even if we know where the students are looking at, we don't know what that means in terms of cognitive processes. It is often very unclear and very difficult to say what this means in terms of cognitive processes, what specific processes are going on whenever a student focuses her attention on a particular part of a representation. And as Stormeyer concludes, one of the most crucial challenges in eye tracking research is to properly link eye movements to these assumed underlying cognitive processes. And today I will show you our attempt to address this issue. That means how we made an interpretation of eye tracking data that considers this relationship between eye movements and what they might mean in terms of cognitive processes. Our research is about functional thinking. And we are particularly trying to see how representations matter for functional thinking. Functional thinking is an approach to early algebra. And very, very briefly, early algebra is one of the aims of early algebra is to prepare elementary students to reason algebraically before the formal study of algebra that starts in secondary school. And one of the ways of doing this is by using the function concept to teach about ways of thinking that are very important in algebra, like generalization and symbolization. And this way of introducing early algebra is known as the functional thinking approach. In the functional thinking approach, there are, the functional thinking approach is moving from a stage of exploration to a stage of application in large-scale interventions that involve, for example, longitudinal designs over different years, and also cross-sectional designs involving different grades in elementary school. And these functional thinking interventions often involve working with problems that integrate text and visual representations like the ones that we are seeing here. In the example at the top, we have this, the situation is explained in text, and there is this pictorial pattern that students tend to use for making sense of the problem in a visual way, for looking at the relationship between the different elements that are described in the text. It's supposed to be a concrete referent for students to work with. In the the other example, we observe a task that is a good example of a typical task of functional thinking instruction. The text presents a situation that can be interpreted from a functional point of view. That is a situation that involves relationships between magnitudes. In this case, it's the relationship between the number of desks and the number of people. And other representations that are there for helping students are this pictorial representation of desks and people, and also tables. Tables are very widely used in functional thinking instruction. I would say that it's the most common form of representation that is employed for introducing functional ideas in elementary school. And this is, of course, very positive because tables are very powerful representations and representational tools that can make transparent abstract ideas, for example, the idea of ordered pairs. However, there are some things that we still don't know about the effects of tables. And for example, like the most common framework for studying how students solve functional thinking problems, functional problems, is this model and this framework that proposes three forms of functional thinking. The recursive form is about noticing change from term to term in a varying quantity. And here we can see an example. In this tabular task, the student had to find the missing number, some missing instances of a dependent variable. In this case, the missing numbers of squares that correspond with a given number of triangles. And this student approached this problem from a recursive point of view, using a recursive form of functional thinking, because he defined a sequence of numbers that increased, but this increase was not was just univariate. I mean, it's a pattern, right? So that's what recursive means. The covariation form of functional thinking is about noticing how two quantities covariate. And here is an example of that. In this case, the student found that the number of triangles increases by 1 in the left column of the table. And he wrote that here, 1, 1, 1, 1, 1, and so on. And he did the same in the other column, in the right column. He found that the number of squares increases by 3, from 4 to 7 to 10 to 13 to 16, and so on. So he did notice that the two quantities changed together. And so that's a covariational form of thinking. The third form of functional thinking is the correspondence form, which is about noticing the relation between a corresponding pair of values. And for example, here, the student found that the relationship between the, the number of triangles and the number of squares can be defined in the following formula. You multiply the number of triangles by 3, and then you add 1, and then you get the number of squares. The correspondence form of thinking it's very important for developing functional thinking, because it's the start of a way of looking at functional data that will allow students to define a formula, which is one way of looking at functions. Functions can be seen as formulas. And a function in this case, a formula, in this case, is a formula that applies to all the pairs, all the instances, all the rows in the table, which denotes, which means that the student is generalizing from a functional perspective, which is the most sophisticated form, or the closest form to a functional way of thinking, which is, for example, different to the recursive form, which is just one variable changing, but the relationship to the other columns is not as clear. I mean, it's just not, it's not a formula, it's not generalizing. It changes in every row. Whereas here is the same formula for all the rows. The functional thinking literature often reports that students tend to struggle to develop a correspondence form of thinking. And one of the most common problems is that students start and get stuck in recursive forms of thinking. It is still unclear whether this is just like whether the students have to start with a recursive form of thinking and then slowly progress to correspondence forms of thinking, or whether these recursive ways of approaching functional data are, or some part of that is a consequence of how tables present functional data. And this is one thing. The other thing is that there might be other forms of representing functional data and functional situations that can help students to see or to achieve a correspondence form of thinking. And our proposal is that we can use diagrammatic tasks for doing that. We thought of diagrams because diagrams have different advantages for facilitating learning. This has been very well documented in the literature. And we know, for example, that diagrams express conceptual relations spatially. They can be idealized or contextualized. They give fast access to meaning, facilitate comprehension, elicit previous knowledge, show physical layouts on how things work, and allow the use of spatial skills. And here you can see one example of the tasks that we use for investigating the effects of diagrams on functional thinking. In these tasks, we can see there's some text that explains the situation. In this case, the situation is a physical situation that that involves the phenomena of shadow casting. The text says, find a pattern linking the height of the pole and the length of the shadow. Choose the option with the numbers missing in the diagrams. The diagram models or represents the shadow casting, a shadow casting situation. We thought this particular situation because almost every elementary student will be familiar with it. Most students have everyday experience with shadows, and they all know that a shadow is a product of the interaction between light and solid bodies. And in this particular case, in our case, the diagram shows a lamp, which is this yellow circle that projects light to a pole. and the pole produces a shadow, which is the gray triangle there. Our diagram has been designed to be as simple as possible. It is very minimal, and if I believe that if you don't have the text, it's going to be very difficult to figure out that these diagrams are about shadow casting. However, that's the point, that you can extract some information from text and another information from diagrams. So the diagram works in a similar way as the tables, in the sense that you have a sequence of numbers that are part of an independent variable, in this case, the height of the pole, and some numbers that are part of the dependent variable, that is the length of the shadow, and some missing numbers of the dependent variable. The task is to figure out which of these options has the numbers that are missing here. And in this case, option A is an option that is congruent with a correspondence form of thinking, in which the correspondence rule in this case is that you add 7 to the number and to the height of the pole, and then you get the length of the shadow, right? So you have 9, if you add 7 to 9, you get 16. If you add 7 to 14, you get 21, and so on. So here, the corresponding numbers are 31, 37, and 45. That's what we would expect. That's the option that students who are thinking about this problem from a functional perspective have to choose, right? That's the option that makes sense. There are other options. The option B, this is consistent with option B is just random numbers, just selected by random and organized just like in an increasing form, but they are not related at all. It's going to be very difficult to find a relationship with the other numbers in the problem. Option C is consistent with a recursive approach. That is, if the student just thinks about the variation in the dependent variable, she will find a pattern that increases by 5 from 16 to 21 to 26 to 31, 36, and 41. That will make sense from a recursive point of view, but not from a correspondence point of view. And option D is consistent with the strategy in which the student figures out a rule for relating the two numbers in the first instance, in the first diagram, and then applies that rule for the missing instance, for defining the missing instances, even if this rule doesn't apply to the other examples. In this case, this rule would be you multiply this number, the height of the pole, by 2, and then you subtract 2, and then you get this number, right? So 2 times 9 is 18, and then you subtract 2, and that's 16. But then you apply that rule, that formula to find these missing numbers, and it would work, right? So that's option D. However, it doesn't work for the other examples. We got this strategy, we observed this strategy in a previous study with paper-based data of students solving functional problems like this one, but in a table. And we found that students do that. They just define a formula that applies for the first pair of numbers, for the first row in a table, but then they just don't check whether that applies to the other examples, and they just apply it to find the missing numbers in the table. And although this means that students have a correspondence point of view, it also means that students are not generalizing. So it's not fully functional. I mean, it is a way of thinking that it's not fully functional because it's not a generalized way of thinking, which is a very important, it's a core aspect of functions. So this is our task. And Um, what I want to emphasize in this presentation is how we thought about this task and how can we interpret how this task actually works in order to make a theoretically driven interpretation of eye tracking data. So for that, we wanted to use a framework for learning with multiple representations. From this point of view, this point of view is about considering representations as cognitive tools that display information to achieve mathematical insight and not only to depict mathematical objects. So students transform representations and work with representations for achieving insight. It's not that representations are there depicting or illustrating something. They are actual tools. And also, from this perspective means that instead of focusing on how students extract information, we emphasize the learning potential of representations by considering their features. So we don't, we try to make not much inferences about the cognitive processes of that students are applying, but instead of that, we try to emphasize the features of representations and in which ways are specific representations contributing to generating insight. And for that, we are employing the framework called the Design, Functions, and Tasks, the DEFT framework, to learning with multiple representations proposed by Sharon Ainsworth. It is a widely used framework for making theorizations and for understanding how representations work. But we found that it's just like not very frequently referred in the mathematics education literature. Although we believe it has a lot of potential, as we can see, as I will try to show you. So in the DEFT framework, the integration of different representations in a task means that representations play different functions. In this case, well, specifically 3 functions. The first function is the complementary functions, which means that representations should complement each other by differing in the information each contains and the processes that each support. In the case of tabular tasks and diagrammatic tasks like the ones that we are proposing, there are 3 forms of representations: text, numbers, and visual components. And text gives you the context and the instruction, that is, text tells the students what to do. So text is there for supporting the process of goal definition. And it's also the process of making a reference. It also supports the process of making a reference to a concrete situation, thereby helping students to make connections between the problem and the contextual knowledge they have from previous experiences. In the case, for example, of the diagrams, well, the text is telling the student that this is about shadow casting. So that's supposed to help the students to make the connection of the problem with previous experiences with shadows. The numbers are representations of quantities and magnitudes, and they are there for supporting computational processes, for defining the rule that governs the relationship between the 2 sets of numbers of the dependent variable and the independent variable. Students need numbers for defining a formula, for defining a function. Numbers are there. Students cannot make computations with text and cannot make computations with the visual elements of the program. So, and also there are, of course, the visual elements of the problem, of the tables and the diagrams. Visual and spatial layouts support processes of establishing relationships and identifying unknowns. That is the process that the processes that lead to the understanding that there are some numbers that are missing there and how to find them. For example, here in tables, the structure of rows and columns should tell students that there is a relationship between, for example, number 6 and number 12. And also that there's a relationship, and then this relationship is the same that connects number 27 with a missing number. And then there are also some missing numbers here that students have to find. These kind of relationships are not this information of how numbers are related to each other in a structure of ordered pairs is not cannot be provided by numbers themselves. For example, if you just present the numbers in a string, I mean, students will not be able to figure out that they have a structure of ordered pairs. And it's also not an information that you can get from text. And in the case of diagrams, this structure of ordered pairs is also presented in a way that the students can see that the numbers in each pair are related visually, right? For example, the height of the pole is visually connected to the length of the shadow. So they are part of the same thing, of the same system, right? And this, again, this is information that you cannot get from text or you cannot get from numbers. Only the visual elements of the problem can give you that information. So text, numbers, and visual elements are complement each other in this way, in these tasks. The other function that multiple representations play are constraining functions. That means that multiple representations help learning when one representation constrains the interpretation of a second representation. In this case, for example, as I mentioned before in previous studies with eye tracking, the text will guide the interpretation of the visual elements of the problem and also of the numerical information of the problem. By explaining the situation and what the students have to do, the text is telling the students how to interpret what they can see the visual elements and the numbers. That's a constraining function of text. The constraining function of number is, as I said before, is just saying, okay, numbers will tell you that there are magnitudes here, and that you should interpret the visual elements as some representations of how magnitudes change. And again, the visual elements should constrain a particular interpretation of data. In this case, the visual elements should constrain the functional interpretation of numerical data. In the case of tables, this should be achieved by means of the structure of rows and columns. And in the case of diagrams, there is the visual elements that connect the numbers in each pair for students is the visual elements that connect the height of the pole and the length of the shadow attached to these numbers. So this representation is constraining a functional interpretation of the numbers. This number 9 relates to 16 in the same way that 14 relates to 21 and 19 relates to 26 in the same way as the examples before, and so on. So that's how these representations constrain the interpretation of each other. Okay, so we made an experiment. We made 2 experiments to find out whether this is the case. Which of these representations, whether tables or diagrams, are better at doing these functions. A third function is constructing function, which is that multiple representations support effective learning when learners integrate information from representations to achieve insights that could be difficult to achieve with only one representation. So in this case, it's about how the different elements of the problem, the text, the numbers, and the visual elements, um, act together or have to be integrated to achieve insight. In this case, a functional insight. So the only way in which students can achieve a functional insight for solving this problem is by integrating, is by putting all the pieces together for constructing a functional correspondence point of view. They cannot do that if one of these three forms of representation is missing. So that's what the constructing function is about. It's about how the students integrate the representations to get an insight. So these are the three functions that, and we wanted to see how tables and diagrams compare with each other in these functions. So we made first a paper-based study. In this study, we presented students with diagrammatic and tabular tasks with or without context. We tested 1,145 students in grade 4, grade 5, and grade 6 in public schools in Mexico. None of these students have algebra or early algebra instruction. We wanted to find which representation eases functional thinking more. And what we found was that diagrammatic tasks were more effective than tabular tasks for easing covariational and correspondence approaches. That is, the students selected the option that was consistent with a correspondence form of thinking more frequently when working with diagrams than with tables, especially if the diagrams had context. And in the case of tables, when tables had context, students selected the recursive option more frequently. So tables seem to prompt, to constrain recursive interpretation of functional data. And diagrams seem to constrain a functional representation of functional data. This is the case when students don't have previous algebra or LD algebra instruction. So that's the first thing that they are going to think about. So, but why? How is this happening? Why do this happen? What do the representations actually do? So we made an eye tracking study, which we wanted to find how do tables and diagrams allocate the attention of elementary students. We tested 60 students in grade 4, grade 5, and grade 6 with the same tasks with context that we employed in the paper-based study. We made this experiment with a portable eye tracker in schools. The schools let us work in a small room, in a private room, in quiet conditions. And we employed a Tobii Pro X230 with a sampling rate of 30 hertz. This means that it's not very fast. However, it gave us a very robust detection of eye movements with unrestricted movement of the head. I mean, students were solving the tasks in a laptop while the eye tracker was just recording their eye movements, and students had the freedom to move their head around and move kind of freely. I mean, they were not like standing and walking or anything, but they were just freely moving. And still, the eye tracker managed to detect their eye movements with very robust accuracy. So what we found first is that we replicated our paper-based study, that is across grades, more functional responses were observed in diagrammatic tasks. We also found that across grades, more recursive responses were given in tabular tasks. So what this means, and also with the eye tracking data, with the eye movement data, we observed that students spend similar amounts of time attending to the two types of tasks. So they didn't invest more time in one or another. And we employed fixation time as an indicator of attention, because this metric indicates that an object is more engaging in some ways. as I said before, it's very difficult to say what this engagement actually means. But that's why we employed the representational framework, to make an interpretation that is based on that theoretical account of how representations work, in order to make some interpretations of how students actually thought about the representations. So first of all, some examples of the kind of fine movements that we observe in these tasks. This is a subject from grade 5 solving a table problem. As we can see, it goes first to the text, and then it's looking at the text, reading it, and then it revisits some parts of the text, and then goes to the data in the table, and also looks at some of the options. It goes back and forth from the table to the options until she selects a solution. In this case, she selected option B, which is the option that is consistent with a recursive mode of thinking. Now, let's see what the student did when reading a diagram. When solving a diagrammatic task, I'm sorry. Here we go. First, again, the student reads the text. And then goes through the visual elements and the numerical elements, and looks around until selects, and then she selects an option. In this case, the student selected option A, which is consistent with correspondence mode of thinking. So this is what the student, this is a still that shows the gaze pathway that we just saw, and we can see how this student concentrated her attention on the first numbers of the dependent variable in the case of the tabular task, and concentrated her attention on the recursive option, didn't look much at the other available options there. So this is what she did in a table. In diagrams, we can see she made a more thorough scanning of the elements in the problem. She went through all the numbers, but also she went through all the options until and of course, she focused more attention on the option that she finally selected, which is the correspondence option. So this is a case that illustrates what happened overall. And our analysis did find that, for this analysis, we first defined what is some areas of interest. We can see here areas A1 and A2 are areas that have the data that corresponds with the independent variable. We defined the areas in the table here, and also the analog areas in the diagrams here. And also we defined area A3 and A4, which is the data from the dependent variable in tables and diagrams, and areas of interest for the response options. In our analysis of fixation durations within each area, so that means how much time did students spend in each of the defined areas of interest. Our analysis of that found that overall, in the table, the students spend more time looking at the numbers in the table, but especially here in the known numbers of the dependent variable. So they concentrated their attention here, as the heat map illustrates. In contrast, in the diagrams, students distributed their attention more evenly across each of the areas with data, and also spent less time looking at the numbers. So That's a difference. That confirms our suggestion that tables, one interpretation of this finding is that tables constrain a recursive interpretation of data. Because even if the text is available, the visual layout of tables makes students interpret the numbers as as a sequence of numbers, the dependent variable numbers as a sequence, not as a set of ordered pairs, just as a sequence with some numbers missing. And that's what they do, and that's why they select a recursive option. And as for the, this is another evidence of this interpretation is in the analysis of fixation times in the response options. We can observe here that in tables, students spend more time looking at the recursive options than to the rest of options. Whereas in diagrams, students spend equal amounts of time looking at recursive and correspondence options than to the other options. So in tables, students mostly focused on looking for a recursive option and did not consider other ones. Whereas in diagrams, recursive and corresponding options were both considered equally. So this is also consistent with an interpretation of how students, how the diagrams did not constrain a recursive interpretation, thereby opening the gates for for other interpretation of the data. For example, correspondence approaches to the data, the correspondence interpretation of the data. So interpretation is like this. First of all, a cognitive load framework would have been problematic. The cognitive load theory is often used in eye tracking studies. In this case, it would have been a problem because diagrams from this cognitive load perspective, diagrams should have produced less functional answers because they have more information. So in a way, they are more difficult to solve. So that would have resulted in a saturation of cognitive resources and then produced less sophisticated forms of thinking, like correspondence forms of thinking. So we believe that the depth framework explains the data with more detail. For example, it says that, as we said before, tables and diagrams complement equally numeric and textual information. So the complementary function is achieved in both cases. However, the constraining function is different in each representation. The visual layout of tables constrain a recursive interpretation of numeric data, even to the point that students neglect the information offered by text. The text tells students what to do and what's the context, which is a functional context, a functional situation. Even like that, the visual layout of table is so powerful that students make a recursive interpretation of the numbers. In contrast, diagrams constrain a more comprehensive processing of the numerical information of the visual elements of the problem and of the context as well. And therefore, that facilitates the insight, that facilitates functional insights and a correspondence perspective on the data. And in the constructing functions, we can say that the layout of tabular tasks can obstruct functional insights by constraining a recursive interpretation, so the construction of functional insights is more difficult. In the case of diagrams, the integration of diagrams, text, and numbers facilitates functional insights. That's what we can do about that. That's our interpretation of eye movements in this study. There are, of course, other important questions, like, for example, whether there is a role of individual differences. We said before that diagrams facilitate the use of previous knowledge. So how does previous knowledge works here in this task? We are in the process of collecting data for answering this question. So just to finish my presentation, I want to say a couple of things about the added value of eye tracking. The first one is that we were able to observe solution processes. That is, we observed how students solve functional tasks with diagrams and with tables without interrupting students. As we saw how the students responded to these problems very quickly in about 2 minutes, 3 minutes at most. And so that's like, we could observe their, uh, how they were scanning these different problems without asking them about that. And we believe that's valuable, especially because these processes of solving, these solution processes were very quick. We also were able to observe non-verbal processes. We were able to observe forms of visualization that support incipient operational processes. For example, the definition of a formula, of a functional formula in an abstract structure of ordered pairs. And for that abstract structure of ordered pairs, students have no words. They don't know. They don't know what they are working with is an abstract structure of ordered pairs. They are just operating on the numbers in a certain way, but they cannot explain that verbally. But we can observe that by looking and analyzing at their eye movements. And we believe thus our study illustrates some of the advantages of using eye tracking methodologies and making representation and interpretation of the data. That's important because eye tracking methodologies produce masses and masses of very fine-grained data. And we need to have a theoretically sound interpretation of those data. Otherwise, it's going to be very confusing. But I mean, as I said at the beginning, we are just learning how to use eye tracking, and I hope this illustrates this process of learning. Well, I would like to thank our sponsors, and if you have any questions or comments that you would like to tell us, please send me an email. Thank you very much. Bye.